Welcome to this interlude lecture on polynomials. This is our second lecture in that sequence. And in this one, we will look at the division with remainder theorem for polynomials. So let us recall the division with remainder theorem for integers. So here is one version of it. Just give me 1 second. Yeah. So suppose we have an integer a and a natural number d. And when I say natural number, I mean numbers of this sort. We do not start with 0, we start with 1 when we say natural numbers. So the division with remainder theorem says that there exist unique integers q and r such that a is equal to dq plus r and r is in this range. So the content of the theorem is that you can write any integer as divisor times quotient plus remainder. So d is your fixed divisor. So what we are saying is that then there exists a unique quotient and remainder such that the remainder is actually a remainder. It is in this range. So that's the content of the theorem. Alright, so we will prove a polynomial version of it. And let us recall some relevant things about polynomials. In the last lecture, we discussed some definitions. Many things were discussed, but here is one particular snippet. For a polynomial, we defined the notion of degree. For the zero polynomial, the degree was set as minus infinite, but for non-zero polynomials, it was the highest power of x for which the coefficient was non-zero. And we saw that the degree of product of two polynomials is the sum of the degrees of the polynomials. Okay, and lastly, every element of the field f can be thought of as a polynomial over f. It can be thought of as a polynomial of degree 0, except for the element 0. If you have the element 0, then the corresponding polynomial is the zero polynomial and its degree is minus infinite. But it is still true that every element of the field f can be thought of as a polynomial over f. Okay. So let us define the notion of division for polynomials. One can guess what the definition is going to be. So we have a polynomial px and a non-zero polynomial dx. We say that dx divides px. We say dx divides px if there is some qx. If there is a polynomial qx over f such that px is dx times qx. Natural extension of the definition of division from integers. So let's see a very simple example. First, let us see a non-example. So let px be something. Let's say x square plus x plus 1. And dx be this polynomial, dx equals x. Okay, so then dx does not divide px. And this is very easy to prove. I will leave this as an exercise. Okay, another example. This is an example in the affirmative. So this time, let us take dx as x plus 2. Or first, let me write what is px. So the px is this. Well, of course, when we were talking about polynomials, I should mention the base field. So base field is reals here and here also reals. Yeah. So let's say px is that and dx is x plus 2. And then dx does divide px. And this is justified by just this simple observation that px is x plus 2 times x plus 3. That's the reason. Okay. And here is some remark about terminology. So if dx divides px, then we also say that px is divisible by dx, or that dx is a factor of dx. Sorry, dx is a factor of px, and also that px is a multiple of dx. Okay, just some equivalent terminologies. Also note that here's a small lemma kind of thing. If dx divides px and px is also non-zero, then the degree of px, or rather let me write it this way, the degree of dx is at most the degree of px. So yeah, this is very, very easy to prove, so I'll leave this as an exercise. Okay, so before we state the division with remainder theorem, we have a small preparatory lemma. Fix a field f and let Rx and dx be some polynomials over f where dx is non-zero. Assume that the degree of Rx is at least the degree of dx. Then there is some capital Qx such that the degree of this thing is strictly less than the degree of R. So as of now, it's unclear why this lemma has to be discussed, but it will be needed soon. And we will just kind of see why this is true by means of an example rather than giving a formal proof. You can write down a formal proof for yourself. So our example is, let's say Rx is, let's say the base field is R and the polynomial Rx is this, and the polynomial dx is, let's say this. Yeah, so here we can see that the degree of Rx is in fact strictly greater than the degree of dx. So how do you find your capital Qx? What you do is you have to multiply it by something so that you end up with a polynomial of degree smaller than Rx. So all we want to do, what we are trying to do is we want to cancel this guy out. I mean, that is our kind of first step. Ultimately, we want to get something of degree smaller than, something of degree smaller than degree of Rx. Yeah, so if we just kind of cancel the leading term, kind of get rid of the leading term, we will be done. So here, if we just multiply by 2 by 5x, then what remains is, if we calculate, what remains is this thing, right? So it's very simple. Just find something for Qx which gets rid of the leading term, and then automatically the degree of the resulting polynomial will be strictly smaller than the degree of the starting polynomial, which is Rx. So that's the idea for the general proof. Okay, so now we move on to the main theorem. So again, we have two polynomials, px and dx, where dx is non-zero. Then, just like in integers, we want to say that there exist unique polynomials qx and rx, such that, again, dividend is equal to divisor into quotient plus remainder, and the degree of Rx is strictly smaller than the degree of dx. Okay? So let's prove the existence first. We want to prove existence and uniqueness, exist and unique, but let's first do existence, which is where the main idea comes. And it is the same idea that you use to establish the same result for integers. So collect all the possible polynomials of this form. So we collect all the polynomials of this form, and if there is something here whose degree is strictly smaller than dx, then existence has been proven, because we will just call it Rx and we will be done. All right. So naturally, we may set, let Rx be an element of S of smallest possible degree. Right? And we would like to show that the degree of Rx is strictly smaller than the degree of dx. So in this statement, we are not saying that there is only one such Rx or anything. There could be multiple such Rx a priori. Just pick one of them. Okay? And so then, by definition of S, Rx is of this form for some Qx. Okay? Or in other words, you can also write that Px is dx qx plus Rx. Okay? So if the degree of Rx were strictly smaller than the degree of dx, we would be done. So assume that degree Rx is at least degree dx, and we want to produce a contradiction. Now by the previous lemma, we can find capital Qx such that the capital Qx in fx, of course, such that this degree is strictly less than the degree of Rx. Okay? But then the degree of, or rather, let's just write this down, Rx minus dx capital Qx, this is nothing but this thing. Right? But now you see, this is something that lives in S, right? By definition of S. And the degree of this is smaller than the degree of Rx by this statement. But what was Rx? Rx was an element of S of smallest possible degree, but we have an element of S with even smaller degree. Rx was chosen so that Rx has the smallest possible degree amongst all elements of S, but here we have created something in S which has even smaller degree, and that contradicts the choice of Rx, and hence this assumption must be false. So the degree of Rx must be strictly smaller than the degree of dx, and hence we have proven existence. Right? All this, I mean, once we have this equation, which is same as this equation, as soon as we had that Rx, the degree of Rx is strictly smaller than the degree of dx, we would be done. So we assumed otherwise and produced a contradiction, and hence existence has been established. Now for uniqueness, whoops, don't have space. Uniqueness is very easy. For uniqueness, let's say we have two different ways of expressing for some Qx and Rx such that degree Rx is strictly smaller than degree dx, and Px is also equal to dx capital Qx plus capital Rx, again with the same constraint. Okay. Now we want to show that for uniqueness, we want to show that little qx is capital Qx, and little rx is capital Rx. All right, but if you just subtract these two equations, the left side will be 0 and what will be the right hand side? We will get 0 is equal to dx times this difference plus this thing, which implies what have I written? Yeah, which implies this. Okay. Now, if this is non-zero, then the degree of the right-hand side is greater than or equal to the sum of the degrees. This is what we recalled in the beginning. Right? But this is at least degree dx. However, degree of the left-hand side. What can we say about the degree of this guy? The degree of the individual things, meaning the degree of capital Rx and small rx, are both strictly smaller than degree of dx, and hence the degree of their difference will also be strictly smaller than the degree of dx. So this is strictly smaller than the degree of dx. So under this assumption, we see that the degree of the right-hand side is at least degree of dx, while the degree of the left-hand side is strictly smaller than the degree of dx. And that would be a contradiction to this equality. And therefore, this assumption that little qx and capital Qx are different is not true. So these two things are equal, and hence this is 0, and hence this is also 0. So what we have shown is that little qx is capital Qx, and as a consequence, little rx is capital Rx, and that's it. That establishes uniqueness. So uniqueness is just like in integers. And here is a corollary of this. It's called the remainder theorem or something. Fix two polynomials over a field f. Again, this is, here we are saying the degree of this guy is 1, so it is automatically non-zero. Then there is some alpha over the field or in the field f such that px is dx qx plus alpha. So you apply the division with the remainder theorem, you will be left with something of degree smaller than degree 1. So that thing is always a field element. A polynomial of degree strictly less than 1 is a field element. In other words, it is just a constant. There is no coefficient of x to the power 1 or x to the power 2 or anything. So only the coefficient of x to the power 0 is there. And therefore, we can just call it a field element. As we said, we can confuse between field elements and the corresponding polynomials that they get. Okay, so I hope the content of this is clear. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.